Alright, so let's consider that we have this question. A compound tube consists of a steel tube, 170 millimeter external diameter and thickness, and 10 millimeter thickness, and an outer brass tube, 190 millimeter external diameter, and also 10 millimeter thickness. The two tubes are of the same length. The compound tube carries an axial load of 1 meganewtons. Carries an axial load of 1 meganewtons. Question says, find the stresses and the load carried by each of the two. Okay, so take Young's modulus of steel as 200 kilonewtons per meter square and Young's modulus of brass as 100 kilonewtons per meter square. Okay, so we have the bars we have in this case are what? Steel and brass. So let's pick out the terms that we need first. First of all, a compound tube consists of a steel tube, 170 millimeter external diameter. So external diameter of steel tube, so DS, capital DS as external is 170 millimeter. And to convert this to meters, we have 0.17 meters. That's simply divided by 1,000. And 10 millimeter thickness. So thickness of steel, okay, call it CS, is actually 10 millimeter. Converting it to meters, we have thickness of steel to be equal to 0.01 meters. If you correct, it's correct, 0.01 meters. So if we have the external diameter and thickness, which means we need to obtain the internal diameter. So to obtain the internal diameter, use the relationship. External diameter D is equal to 2 times thickness plus internal diameter of steel. Okay, so that means to obtain the internal diameter of steel, ds will now be equal to, so we send 2 thickness over to the equation. We have the internal diameter of steel minus 2 times thickness of steel. So the internal diameter of steel is simply, external diameter was given as 0.17 minus 2 times thickness is given as 0.01. Okay, so ds is actually 0.17 minus 0.02. That should be 0.15. So which implies that the internal diameter of the steel is actually 0.15 meters. So that gives us the internal diameter of steel. Okay. Also, we are given that an outer brass tube, 190 millimeter external diameter. So the external diameter for the brass tube, external diameter of brass, that's capital D is given as 190 millimeter, which is equivalent to 0.19 meters. So this is the external diameter of brass. And the thickness of brass is also 10 millimeter and 10 millimeter thickness. So thickness of brass is also 10 millimeter. Okay, thickness of brass TD is also 10 millimeters. So that implies that thickness of brass is actually 0.01 millimeters. So to obtain the internal diameter of brass, we also use the same relationship. Internal diameter of brass, we have small d, so DE is now equal to capital D, which is the external diameter of brass, DB minus 2 thickness of brass. Okay? So the internal diameter of brass is equal to 0.19 minus 2 times 0.01. And and it is actually 0.19 minus 0.02. So that means the internal diameter of brass BE is actually 0.19 minus 0.02, that's 0.17. 0.17 millimeters. You guys are following me? Okay, 0.17 millimeters. So if you have that original diameter of brass, okay. So let's find the area. Okay, let's look at this one. First of all, we'll apply the compatibility equation. From compatibility equation, we have that the strain of brass must be equal to the strain of steel. Okay, the strain of brass must be equal to the strain of steel. But you know that strain itself is equal to stress all over Young's modulus. So that simply implies now that the strain of brass becomes stress of brass all over Young's modulus of brass. And that's equal to the stress of steel all over Young's modulus of steel. Okay, so we are given the Young's modulus of brass and Young's modulus of steel from the question. Young's modulus of brass was given as 100 giganewtons, while that of steel is 200 giganewtons per meter square. Okay, so let's substitute that in the equation and see what we have. This will give us stress of steel, stress of brass, all over 100 by 10 raised to power 9 to be equal to the stress of steel all over 200 by 10 raised to power 9. So if we do the same analysis we did in the previous question, let's cross multiply. This man multiplies the top. Okay, but we leave stress of steel behind. Let's leave stress of steel subject to the formula. So we are multiplying 200 to multiply stress of brass. So you have that stress of steel is now equal to 200 multiplied stress of brass all over 200 by 10 raised to power 9 by 10 raised to power 9 multiplied stress of brass all over 100 by 10 raised to power 9. So this simply implies that stress of steel is actually 200 by 10 raised to power 9 divided 100 by 10 raised to power 9 will give us 2 times stress of brass. So call this equation call this equation 1. So from equation 1 we obtain that stress of steel is actually 2 times stress of brass. So we'll keep it there. The next equation is that from the load equation, are you there? Are you lost? Are you lost? From here, just cross multiply. Okay. So from the load equation, we have that load carried is equal to the load of steel plus load of brass. That's the load equation. Load carried is equal to load of steel plus load of brass. And load carried in this case is 1 meganewtons. It was given in the equation that load carried is the two carries an axial load of 1 meganewtons, and mega means 10 to the power 6. So the load carried is actually 1 by 10 to the power 6 equal to load of steel plus load of brass. But load itself is simply stress times area. Load is simply stress times area. If that's the case, then 1 meganewton 1 by 6 10 to the power 6 is now equal to the place of load of steel. You have stress of steel times area of steel plus in place of load of brass you have stress of brass times area of brass. So let's call this equation 2. Now let's find what the areas are. Area of steel AX is simply pi over 4. Since it has both internal and external diameter, it becomes external diameter square minus internal diameter square. You have that. So therefore, area of steel is simply pi is 3.142 divided by 4. External diameter of steel gives us 0.17. External diameter of steel is 0.17. So 0.17 squared minus internal diameter is 0.15 all squared. So area of steel is equal to 3.142 divided by 4.
0.7855.
0.7855.
Yes.
Okay. Open brackets. 0.17 squared.
0.0289.
0.0289 minus 0.15 squared.
0.0225.
0.0225. Okay. Area of steel is equal to 0.7855 multiply 0.0289 minus this.
6.4 times 10 to the power minus 3.
6.4 by 10 minus 3. So multiply by 0.7855. So that simply implies that the area of steel is equal to multiply by 0.7.
5.0272 times 10 to the power minus 3.
5.0272 or 0.0275 per minus 3 in meter square. So this is the area for steel. So we also now obtain the area of the brass. We now obtain the area of the brass. Okay, so area of brass is also that AB is also pi over 4 external diameter square minus internal diameter square. So area of brass is 3.142 divided by 4 into external diameter of brass is 0.19 square minus internal diameter is 0.17 square. So area of brass is now equal to 0.7855. So 0.19 square.
Zero 0.19 squared is 0.0361.
361
Yes, sir.
minus 0.17 square.
Minus 0.17 squared.
Just 0.2.
0.2. 0.0289.
Is 9. Okay. So area of brass is equal to 0.7855 multiply 0.0361 minus 0.0289.
7.2 times 10 to the power minus 3.
So multiply by 0.7855 and area of brass is equal to
5.6556 times 10 to the power minus 3.
66 by 10 to the power minus 3. So this is the area of the brass. So knowing the two areas, we substitute that into equation 2 for in place of the areas. So substitute AX and AB. Substitute area of steel and area of brass into equation 2. We have 1 by 10 to the power 6 is equal to sigma B, right? So sigma x less of x steel times area of steel. Area of steel is given as 5.027 by 10 to the power minus 7. So we have in place of area of steel 5.027 by by 10 to the power minus 3 times stress of steel plus the area of brass is 5.66 by 10 to the power minus 3 times the stress of brass. So this is what you have in that equation. But recall, but sigma x from the equation is it 2? From equation 1, sigma x is equal to what? 2 times sigma b. That stress induced in the steel bar is twice stress of the brass. Okay? So from equation 1, sigma x, that stress of the steel, is equal to 2 times stress of the brass. So in place of sigma x in this equation, we put in what? 2 sigma b. Is that clear?
Yes, sir.
In place of sigma x, we put in this value. So that means we have 1 by 10 raised to the power 6 equal to 5.027 by 10 raised to the power minus 3 multiplied by, in place of sigma x, we have 2 sigma b. 2 sigma b. Okay. 2 sigma b then plus 5.66 by 10 raised to the power minus 3 sigma b. So now you do 2 multiplied by 5.027 exponential minus 3. So you have 1 by 10 raised to the power 6 equal
So I say
5.027 by 2. 5.027 exponential minus 3 multiplied by 2.
0.010054.
0.01.
0054.
Keep that 0.01. Sigma b plus you have x to be 5.66 times 10 minus 3 sigma b. So at this point now you can add. They have the same sigma b and sigma b, so you can add them together. 0.01 plus 5.66 exponential minus 3. 1 by 10 is equal to now equal. So add them.
0.01566.
0.01567 sigma b. So it becomes easier now for us to find the stress induced in the brass. So stress of the brass, we divide this out. So we make sigma b solve the formula. It becomes 1 by 10 raised to the power 6 divides 0.0157. 0.57. So that means stress in the bar, in the brass bar, is actually given the division.
63694267.
636942
67.52.
0.52.
Yes, sir.
Okay, newtons per meter squared. So we can approximate to mega. Sigma b is actually, so let's move 6 steps backward. 1, 2, 3, 4, 5, 6 becomes 63.69 mega newtons per meter squared. So that's stress in the brass. Then we have to obtain stress in the steel from equation 1. From equation 1, recall that stress in steel is 2 times the stress in the brass. So that simply implies that stress in steel is actually 2 times 63.69. What do you have? 2 times 63.69.
127.38.
127.38 mega newtons per meter squared. So that's the stress induced in the steel bar. The next question, so we should find the loads carried by each of the materials. So we find the loads carried by each of the bars. Can I write them? So you already know that load, which is P, load of brass is simply stress of brass times the area of brass. So therefore, load of brass will now be stress of brass gave us 63.69. So we have 63.69 by the area of brass. Area of brass gave us, okay, 5.6 is exponential minus 3. So now 5.66 by 10 to the power minus 3. So that means the load of brass is equal to, give me this value, 63.69 by 5.66 exponential minus 3.
5.66 exponential 3. 0.3604.
0.36. Okay, this 0.36 mega newton, because this is mega newton. Okay, 0.36 mega newton. You can read it like that if you want to convert 1 to 3. Or you can also be written as load of B is 36 kilo newtons, 36 kilo newtons. Can be called 36 kilo newtons. If you move it 3 steps backward, 1, 2, 1, 2. Okay, 360 kilo newtons, sorry. Move it 3 steps forward to give you 360 kilo newtons. 1, 2, 3. Okay, so that's the load carried by brass. Meanwhile, load carried by steel, still the same thing. Load for steel, load carried by steel, Px is also sigma x times area S. And the stress of steel is given as 127.38, 127.38, multiplied by area of steel is 5.027, 027 by 10 raised to the power minus 3. So load of steel is equal to 127.38 times 5.027 exponential minus 3.
0.640339.
0.64 mega newton. So you can also move this forward. 1, 2, 1, 2, 3. 3 steps forward. You can do it as 640 kilo newtons. So that is the stresses and the load carried by the compound brass. It's simple, I think. It's simple. It's simple. It's simple. Just